In this video, I'm going to cover example 3 for Thevenin and Norton equivalent circuits. The problem statement asks us to find the Thevenin and Norton equivalent circuits if the 17 ohm resistor, which is right here, represents the load resistance. Now, as always, if the problem statement specifically states that there is a load present in the circuit, then the load resistor is not part of the analysis. So we remove that, okay? And then we begin our analysis without that 17 ohm resistor. Once we remove that resistor, we can see our terminals of analysis are right here, A and B. So what I'm going to do is I'm going to draw out the circuit without the 17 ohm resistor and just extend terminals A and B to give you a better idea of how to set up this circuit. So let's see. We have a 20-volt source on the left, plus minus 20 volts, 5 ohm resistor, a 20 ohm resistor from the top, and then this crosses over into the 10 ohm resistor. And then we also have a 1.5 amp current source with current going towards the right. And let's extend out. Let's extend this out. And of course, 17 ohms is no longer part of our analysis. 5 ohms, 20 ohms, 10, and this is 1.5 amps. 20 volts. Okay, terminals A and B. Let's use red, A and B. Okay, so this is a circuit we need to modify 3 times to find our 3 quantities. Thevenin voltage, Thevenin resistance, and our Norton current. Okay, Norton current. All right, so let's begin. Let's start with Thevenin resistance. Well, for RTH, the first thing we need to do is we need to reduce all independent sources to 0. Reducing a source to 0 means replacing a voltage source with a short circuit and a current source with an open circuit. So we redraw the circuit, and all we are left with in the circuit are the 3 resistors. The current source is, of course, gone. It's an open circuit. No need to draw that. This is 5 ohms, 20, and 10. So as with the previous problem, in the previous example, we saw how a short circuit brings a resistor in parallel, and we have the same instance or the same thing happening here. Because of the short circuit of this voltage source, right here on the left, the 5 ohm resistor is now in parallel with the 20. And so RTH, as measured between the terminals A and B, let's say REQ, measured between A and B, can be written as 5 in parallel with 20, which would then be in series with the 10. That gives me 5 times 20, 100, divided by 5 plus 20, which is 25, plus 10, and final REQ value of 14 ohms. 14 ohms. Therefore, my Thevenin resistance RTH, which is equal to REQ, is 14 ohms. Okay. So 1 quantity done, 2 more to go. Now, let's look at VTH, Thevenin voltage. And I would repeat again here, determining Thevenin voltage has nothing to do with the circuit on the right. We forget about that. And we go back to our original circuit. And this time, of course, we have our sources in there. Without a source, we would not have any voltage or current. And so we redraw the original circuit with both the sources back in. And this time we want to find the open circuit voltage at our terminals of analysis. Terminals of analysis, of course, A and B. Current source, 1.5 amps, 10 ohm resistance, 20 ohm resistance, 5 ohm resistance, and 20 volt source. And then terminals of analysis A, B, and we wish to find the open circuit voltage between these terminals. The polarity, of course, plus at A minus at B. That is how we would solve this. So that is the setup of the problem. Now, at this point, you can choose which analysis technique you wish to use. You can choose mesh current analysis, node voltage analysis, superposition, or anything else that strikes your fancy. So let's see. I would choose, well, just for the heck of it, I'll choose node voltage analysis. Okay, node voltage analysis. But you are free to choose whichever technique you wish. I'm going to solve this with node voltage. So node voltage analysis, of course, we choose a reference node first. So I'm going to choose this bottom node as my reference node. Keep things simple because we have a voltage source connected there. And so I automatically have an answer for the node here. And if I say, since I already have terminals A and B, what I will do is I will choose, let me continue with the same naming convention, and I will choose C over here, and the other node is D over here. There are no other nodes in that circuit. The current source is connected between A and D. Okay, so keep that in mind. All right, so now I have A, B, C, D. B is my reference node. Again, B is my reference node. I wish to find VA, right? If B is my reference node and I wish to find the voltage between A and B, automatically it means VOC is equal to VAB. Or since B is my reference, I can write it's just VA. So I find voltage at A, node A, VA, and that would be my open circuit voltage, which would be my Thevenin voltage. All right. So the two unknowns in the circuit are A and D. VC, since B is my reference, let's see, actually, let me write this down. B is reference, or I chose B as reference. So VB is equal to 0 volts. And from there, it follows my open circuit voltage VOC is equal to VA. And then also follows that VC is equal to 20 volts because the 20 volt source is connected between C and B. All right, so VC is 20 volts. Last thing to do for problem setup is to assign branch currents. So I have 3 resistors, all this I1. Then current for 20 ohms is I2, and current for 10 ohms as I3. And this presents a very interesting case. Okay, if we look at just the current source connected between D and A, what do we see? We see that A is open circuit. It's not connected to anything except the resistor and the current source. So the current source has nowhere else to go except through the 10 ohm resistor. And so I can write I3 is equal to 1.5 amps, right? There is no other pathway for that current source to flow through. So I3 is equal to 1 amp. 1.5 amps. Now, if I write KCL at node D, KCL at node D, I have two currents entering. So I1 equals, well, actually I1 plus I3. I1 plus I3, two currents entering, and then one current leaving. So I1 plus I3 equals I2, right? Now, I1 plus I3 is equal to I2. Let's see if I did it right. Oh, no, I also have to account for the current source leaving. So it has one current entering right here, another current leaving, and this entering. So I have four currents entering, I have two currents entering and two currents leaving. So I have to write I1 plus I3 equals I2 plus the 1.5 amp current source. Okay. And that is the correct equation. Now, because I3 and 1.5 is the same, they cancel each other out. And I'm left with I1 equals I2. Right? I1 equals I2. And if I1 equals I2, I apply Ohm's law and expand it in terms of the node voltages. I get VC minus VD divided by the 5 ohm resistor. And this would be equal to I2, which is VD minus VB divided by the 20 ohm resistor. All right. VB is a reference node. That is 0. That goes to 0. I'm going to multiply both sides by 20. If I do that, I get 4 times VC minus 4 times VD equals VD minus VB. Well, VB is 0, so that's gone. I have 4 times VC, which is, C is 20 volts. So I have 80 equals 5 times VD. And therefore, VD equals 16 volts. VD equals 16 volts. Now that I have the node voltage at node D, I can write an expression for I3. I'll plug in the values for the current I3 and then find the node voltage for VA. Now, I3, I can write in terms of the node voltages A and D expressed with Ohm's law and the 10 ohm resistor. Okay. So if you look at the diagram clearly, 10 ohm resistor is connected between nodes A and D, and I3 is flowing between those terminals. It is flowing from right to left. So automatically the logic follows. VA is higher. If VA is higher, I can write an expression for I3 as too many glitches. All right. I3 can be written as VA minus VD divided by the 10 ohm resistance. And I3 is already known to us. So I can write 1.5 amps is equal to VA VA minus VT. So VA minus 16 divided by 10. I rearrange the terms and I obtain VA as 31 volts. 31 volts. And therefore, my Thevenin voltage, which is equal to VA, is also 31 volts. You can try and solve this using mesh current analysis, and you should obtain the exact same answer. Okay, should obtain the exact same answer. So VTH, the Thevenin voltage, is the voltage measured at node A if my reference is at node B. So it automatically gives me an answer. And as I said, you can solve this using mesh current analysis. You could also solve this using superposition principle. And if your calculations are correct, then your answer should be 31 volts. All right. Then let's find our last remaining quantity, which is the Norton current. Okay, Norton current. And so for Norton current, I'm going to draw out a line right here. And this off. All right. Okay, so Norton current requires a short circuit between our output terminals, the exact same circuit, 20 volts, resistor, resistor, resistor. And this time, of course, 1.5 amps, 20 volts. This is 5 ohms, 10 ohms, and 20 ohms. I need to have a short circuit wire running between A and B. This is A, this is B. The current always flows from top to bottom. Okay, that is my short circuit current, ISC. So I'm going to choose, let's see, mesh currents in a clockwise direction. And because we have a current source in there, oh, sorry, should have started off with this. I'm going to choose MCA, mesh current analysis, to solve this. Okay, I choose MCA, but you can choose node voltage. You can choose anything else you want. If you choose node voltage, I think it might be easier because you have, let's see, A and B are now one nodes, right? Because of the short circuit. So if you choose that as your reference node, well, actually, we can't choose that as a reference node. That might be a little bit more involved solution. So I'll come back to that later. Let's stick with mesh current analysis for now and solve this. So I can see that I3 is the same as the 1.5 amp source. So I can automatically write that I3 is 1.5, right? I can write I3 is 1.5. So I already have the answer for one of my mesh currents. I3 is 1.5 amps. Furthermore, ISC is the same as mesh current I2. So if I find the value for I2, that would be my ISC. Again, it is not shared with anything, and so I can straightforward write that. All right. Okay, so let's apply KVL in mesh 1. It's mesh 1, mesh 2, and mesh 3. If I apply KVL in mesh 1, I can see I have three quantities. I have the 20-volt source, I have the 5-ohm resistor, and I have the 20-ohm resistor. So 3 voltage drops, and I'm going clockwise from the bottom left of the circuit. So I have minus 20 plus 5 times I1 plus 20 times I1 minus I2 equals 0. Okay. All right. So to reduce this equation, rearrange the terms, and I get 25 I1 minus 20 I2 equals 20. I am able to reduce this further, and so I'll go ahead and do that. I will get 5 times I1 minus 4 times I2 is equal to 4. And I'm going to call this equation 1. Okay, equation 1. Then I'll go ahead and apply KVL in mesh 2. I wouldn't need to apply it in mesh 3 because there's a current source in there, so I would not be able to describe the voltage drop across it. And even if I wanted to, the voltage drop across it would be the same as the voltage drop across the 10 ohm resistance. And so that would simply be the same voltage because it's in parallel. So anyway, KVL in mesh 2, I'm going to write first starting from the bottom left. I have two resistances, 20 and 10 ohms. So I would have a voltage drop for the 20 ohm resistor. And this time, because I'm in mesh 2, I2 is positive, I1 is negative, and then the 10 ohm resistor has a voltage drop, again, I2 positive and I3 negative. That would be equal to 0. Expand the terms and reduce the equation, and I would get 20 times I2 minus 20 times I1 plus 10 times I2 minus 10 times I3 is equal to 0. Now, I3, of course, is 1.5 amps. So that comes out to be 15. I rearrange the terms, take 15 on the other side, and I can write minus 20 times I1 plus 30 times I2 is equal to 15. And I'm going to call this as equation 2. I can solve this with any method. You can solve this directly by using an online solver. You can use your programmable calculators, or you can solve it manually, like I do. What I'm going to do is I'm going to take equation 1, multiply it by 4. If I multiply it by 4, I get, what do I get? It gives me 20 times I1 minus 16 times I2 is equal to 16. Let's call this equation 3. And then I will take equation 2. Oh, I hate when this happens. Okay. Equation 2 plus 3. And that gives me 14 times I2, 14 I2 equals 31. Right, 14 I2 is equal to 31. and therefore I2 is 2.2142 amps. And we had already established our Norton current, of course, is ISC. We had already established that ISC is the mesh current I2. And so my Norton current is 2.2142. And that is my answer. Let's go ahead and verify that using Ohm's law. Let's see if that works. By Ohm's law, I should have VTH equals IR, so IN times RTH. It's 2.2142 times 14, which gives me 30.99 volts, which is close enough. VTH. And then the final Thevenin circuit and the final Norton circuit. The final Thevenin circuit is, of course, the Thevenin voltage in series with the Thevenin resistance. RTH is 14 ohms. VTH is 31 volts. And I plug the resistor back in, the 17 ohm resistor. And my terminals A and B. And similarly, the final Norton circuit will have a current source in parallel with a resistor. That is the Thevenin resistance, RTH, 14 ohms. Current is going in the upwards direction. In order for it to go down into the 17 ohm load. Again, remember, current is being delivered, so it has to be going down because this current goes down, so logically it follows that this current has to go up. Okay, so always keep track of your current directions. It's 2.2142 amps. And that's it. Of course, my terminals A and B. Oh, I hate when this happens. Right. So there you have it. Final Thevenin circuit, final Norton circuit. VTH 31 volts, RTH 14, Norton current 2.2142, and again in parallel with the RTH and 17 ohm resistance. That is the Thevenin and Norton equivalent network for example 3.